Ever get that feeling where you just want to dive right into something really cool? Like learning how to make your own camera with a tiny computer. But like, who's got the time to read through pages and pages of instructions?
Yeah, definitely. It can be daunting, especially when you see all these incredible projects popping up using these little Raspberry Pi camera modules. It's like, where do you even begin?
Right? That's exactly why we're here. We're going deep, deep into the world of these Raspberry Pi cameras. Not just the basic stuff, but a real look at how to use them, what they can do, all the way to some seriously inspiring projects.
Absolutely. And we're not going to get lost in all the technical jargon either. We've been poring over the official Raspberry Pi camera guide, really dissecting it.
So whether you're a complete beginner or you've already dabbled a bit, this deep dive will give you a clear roadmap. We'll cover the original camera module, the V2, and of course the game changer, the high-quality camera, the HQ camera.
That's right. It's fascinating to see how they've evolved. The original module came out back in 2013, a real pioneer. Then, in April 2016, we got the camera module V2, a big step up in performance.
And then, in April 2020, boom, the HQ camera hit the scene, and it really shook things up.
It did. Higher resolution, of course, but the interchangeable lenses, that's the real game changer. They actually have dedicated 6mm and 16mm lenses specifically designed for it. And don't forget about the Ultra HD image capability. It's a beast.
So what's the big deal about those interchangeable lenses? I mean, what can you actually do with them?
Well, think about it. With a wide-angle lens, you can capture a much broader scene. Super useful for things like security cameras. On the other hand, you can grab a telephoto lens to zoom right in on distant objects. Imagine that for wildlife photography, right from your Raspberry Pi.
That makes a lot of sense. It's all about matching the lens to the task.
Exactly. But the core concept is the same across all these modules, taking a Raspberry Pi and turning it into a pretty impressive digital camera.
Awesome. So today we're going to break down getting the camera physically connected, getting into the command line control, which honestly is way more powerful than you might think. Then we'll jump into Python programming for more advanced stuff. And yeah, we can't forget time-lapse and those amazing slow-motion shots.
Definitely not.
And we'll definitely wrap up with some of those mind-blowing projects that really showcase what this technology can do. Are you ready to get started with the physical connection?
Let's do it.
So it all starts with this ribbon cable. All the Raspberry Pi camera modules connect to the Raspberry Pi's dedicated camera port, and sometimes call it the CSI port, which is short for Camera Serial Interface, a super fast connection just for these modules. You connect it using this flat ribbon cable. Just remember, handle the little plastic flap on the port with care. Just ease it upwards, don't force it.
Right. And when you're sliding that ribbon cable in, make sure you get the orientation right. Usually, if you've got your Raspberry Pi with the HDMI port facing you, the side of the cable with the metal connectors should be facing the same way as the HDMI. That blue plastic stiffener goes on the other side. Slide it in gently, make sure it's straight, and then carefully push that plastic flap back down to lock it in.
Great point about the orientation. It's also worth mentioning, for folks using a Raspberry Pi Zero, that camera port is a different size. So you'll need a special adapter cable to hook up the standard camera ribbon cable to the Pi Zero's port.
Absolutely. Once you've made the physical connection, you've got to tell your Raspberry Pi's operating system, usually Raspbian, that a camera is there. You do that by going to the Raspberry Pi icon at the top left of your screen, then to Preferences, and then select Raspberry Pi Configuration. In the window that pops up, click the Interfaces tab. You'll see an entry labeled camera.
Okay, I see it.
Click the Enable button next to it. Then the system will ask if you want to reboot. Make sure you hit yes and let it restart. That reboot is super important. The changes won't take effect, and the camera won't be recognized properly without it.
Got it. So the camera's connected and enabled. How do we actually take our first picture?
The simplest way, using the command line. Open a terminal window on your Raspberry Pi and type in the command raspastill-o test.jpg, then hit Enter.
What happens when I hit Enter?
You should see a live preview pop up on your screen for about 5 seconds. It's just a quick view to check your composition. Then the camera snaps a picture and saves it in your home directory as test.jpg. If you want to take another one, type the same command again. Just don't forget to change the output file name, the part after the OO. If you don't, each new picture will overwrite the last one.
So simple. Now, you mentioned another command earlier, something about...
Raspiev, yeah. That one's for getting into the nitty-gritty of the raw data from the sensor. It takes the unencoded YUV or RGB data directly from the camera and saves it to a file.
YUV and RGB. What's the difference?
There are different ways to represent color information in an image. YUV. It separates brightness from color, useful for certain video processing tasks. And if you want RGB output specifically when using Raspbian, just add the RGB switch to the command. This raw data format is usually for more specialized stuff when you need that unprocessed information, not just a compressed JPEG.
Interesting. Okay, so we've got the basics of taking pictures down. But what about having more control over the image? I'm guessing these cameras, even though they're small, have settings like brightness and exposure, just like a regular digital camera, right?
Oh, absolutely. The command line tools give you a surprising amount of control over all sorts of image parameters. Let's start with the preview window. Say it's upside down, just add the default 180 switch to your Raspastill or Rasputin command, and it flicks it right back. The same if you need to flip it horizontally or vertically, like if your camera's mounted upside down. Dash HF for horizontal flip, dash VF for vertical. You can even use both.
So many options. What if I want the preview to fill the whole screen?
Easy. Just add the iOS switch to the command for a full screen preview. You can also play with the preview's opacity, make it more or less transparent, using the X switch and a value between 0, totally invisible, and 255, totally opaque.
Okay, and if I just want to get rid of the preview altogether, like maybe I have a script running in the background and don't need it?
Just use the high switch and it's gone. Now, for those camera settings you were talking about, you can change the brightness of the image with the taskbar switch. It ranges from 0 to 100, 50 being the default. Contrast is controlled with ESCO, ranging from -100 to 100, with 0 as the default.
Makes sense.
Yeah.
What about sharpness?
For that, you use the hive switch, again, -100 to 100, and 0 being the default. Same range for saturation, controlled with ISA. And then there's ISO sensitivity, how sensitive the sensor is to light. That's controlled by ISO. You'll usually use standard values like 100, 200, 400, 800, that sort of thing. And for fine-tuning the exposure, there's EV compensation using the IVE switch. It goes from -10 to +10, so you can tweak the brightness up or down.
So much control right from the command line.
Yeah, it's really cool. And on top of that, you have preset exposure modes for different scenarios. You access them with the X switch, followed by the mode. You've got auto, which is the default, night for low light, night preview for optimizing the preview in the dark, backlight for when you've got a subject against a bright background, and there's spotlight, sports for fast action, snow, beach for those bright reflective scenes, very long for really long exposures. Oh, and fixed FPs, that's for video at a constant frame rate, anti-shake to minimize blur from movement, and even fireworks.
Wow, so many options. I mean,
Yeah.
you can really dial in the perfect settings for any situation. What about white balance? That's important for getting the colors to look right.
You got it. Use the op switch and pick from different options. Off turns off automatic white balance, though you don't get direct manual control from the command line. Auto is, well, automatic and the default. Then you've got presets for different lighting. Sun, cloud, shade, tungsten. That's for those old incandescent lights. Fluorescent, incandescent for warm indoor lights, flash, and horizon. Picking the right white balance makes sure whites actually look white and the colors look natural under all sorts of light. Like, if you're filming inside with tungsten lights, picking the tungsten AWB preset should give you much better color than just leaving it on auto, which might make everything look way too yellow.
Okay, so many things to keep in mind. Now, what if I want to set the shutter speed myself?
You can. Just use the S switch, followed by the duration in microseconds. Just remember, the maximum shutter speed you can use depends on things like the exposure mode and other camera settings. For metering, how the camera judges the light to get the exposure right, you use Malone with options like average, the default spot, which just looks at a small area in the center, backlit, which makes sure the foreground is exposed properly when there's a bright background, and matrix, which looks at the light across the entire frame.
Wow, so many ways to fine-tune everything. What about this region of interest I saw mentioned?
Yeah, that's the S-ROY switch. Really powerful stuff. It lets you tell the camera to focus on a specific rectangular area for metering, maybe even focus, though that's fixed on the standard modules. You define it with 4 numbers between 0.0 and 1.0 X and Y coordinates of the top left corner. Then the width and height of the region, all relative to the whole sensor, like S-ROY 0.5, 0.5.25, 0.25, with center region that's 25% of the width and height of the sensor. Really helps to get the exposure just right for a particular part of the scene.
I can see that being super useful. Okay, what if I want to take a picture at a very precise moment? Like, I don't want to rely on a timer or anything.
Key press mode is perfect for that. Just add the -K switch to your Raspastill command, and the preview will pop up. Now, the camera will only take a picture when you press the Enter key. Your Enter key becomes a manual shutter button. To get out of key press mode, press X, then Enter.
So I can basically line up the shot perfectly and then click. What about taking multiple pictures in key press mode?
You can do that too.
Yeah.
If you put Subbureau 4D in your output file name, like this, Raspastill, Jasho, Keypress, Vero4D-AGD-KIOK. Each picture you take gets saved with a 4-digit number at the end. So first press of enter saves keypress 00000.jpg, second saves keypress 00000.jpg, and so on. Really useful for capturing a series of shots or, building those time-lapse sequences we'll talk about later.
Nice. Okay, let's talk about image effects. What kind of creative things can we do?
You're in for a treat. There are tons of built-in image effects you can play with. Just use the ifx switch in your Raspastill command, followed by the name of the effect. You've got none. The default negative, solarize, posterize, sketch, denoise to get rid of noise, emboss, oil paint, hatch, Drpen, that makes it look like a pencil drawing, pastel, watercolor, film for that cool film, grain, blur, saturation to change the color intensity, kind of like the teller switch, but as an effect, color swap, washed out, color point to make one color pop, color balance, and get this, cartoon. You even see the effects live in the preview.
That's awesome. No need to edit the pictures afterwards. Now, what about just plain black and white?
For that, you use the DexCFX or color effects switch with this specific setting, DexCFX 128.128. Basically, you're telling the camera to give equal weight to red and blue, and that ends up with a black and white image.
Super cool. Oh, and I saw dynamic range compression mentioned. What's that all about?
Dynamic range compression, or DRC, you turn it on and off with the dice DRC switch. It's a way to bring out more detail in both the really bright and really dark areas of a high contrast scene. When you have those super bright spots that are just white and the really dark spots where you lose all the detail, DLC tries to balance those extremes so you can see more in both areas. Really handy when you've got a lot of variation and lighting. It's off by default, though.
That makes a lot of sense. So those are the general controls, right? What about options specific to taking photos with Raspastill?
We already talked about ASHO for the file name and ASH for a delay in milliseconds before the picture is taken, like a self-timer. But you can also set the width and height of your picture in pixels with the DIO and IH switches. Just remember, each camera model has a maximum resolution. The HQ camera goes up to 4.56 by 3040, the V2 to 3D280 by 2464, and the original V1 to 2592 by 1944. You can even tweak the quality of the saved JPEG with MashU from 0, which is the most compressed and lowest quality, to 100, the least compressed and highest quality. And if you need a lossless image format, you can save as a PNG using the ePNG switch.
Okay, all that's for still photos. What about shooting video with the Raspivid command?
When you're recording video, use -T to set the duration of the video in milliseconds. Then you control the bitrate, which determines the video quality and file size, with -B. You set the value in bits per second, so for 15 megabits per second, it'd be -B 1500,000. -PS sets the frame rate, which affects how smooth the motion looks in the video. It's always a good idea to check Chapter 17 of the official guide for the maximum bitrate and frame rates for your specific camera model at different resolutions. So, to record a 5-second video at 1080p resolution, that's 1920 by 1080, with a bitrate of 15 million bits per second and a frame rate of 30 frames per second, you'd use the command. Raspivid -B 105,000 non-C 100 0000000 to 30 ash of video.h264. That saves it in the h.264 format with the file name you put after the ash.
Awesome. We've got the basics of taking photos and videos down. What about creating those cool time lapses where you see those long, drawn-out events compressed into a short video?
Time-lapse photography. Such a cool technique. It's taking a bunch of pictures at regular intervals and then stitching them into a video. When you play it back, you see that long process compressed into a much shorter time, so a flower blooming or clouds moving looks sped up, like it's happening really fast.
Right. So the first steps are just like setting up for regular photography, camera connected, enabled in Raspberry Pi configuration, maybe take a test shot just to make sure everything's working.
You got it. Always power down your Raspberry Pi before connecting or disconnecting that ribbon cable from the camera port. Once it's enabled and rebooted, a simple raspastill-o testimage.jpg command is a good way to make sure the camera's working. And hey, remember, if it's upside down, Nairot 180 will fix it.
So how do I tell Raspastill to take those pictures automatically for a time lapse?
The magic switch is -O. You follow it with a number in milliseconds that says how long to wait between each shot. So to take a picture every 10 seconds for 3 hours, you'd use a command like this. Sudo raspastill nachash w 1920 nasha pt 1080800 1000 c1 800,000 one way nlt 10800,000 no 10 lt our first tmo frame 1042.jpg and n.
Okay, let's break that down. That.w 1920 out of 1080 sets the resolution. NASA 1/800,000 is the total recording time, 3 hours in milliseconds, 3 hours times 60 minutes an hour times 60 seconds a minute times 1,000 milliseconds a second. NASA low 10,000 is our 10-second interval, 10,000 milliseconds. That'll valro TML frame present 04d.jpg tells it where to save the pictures.
But what about that %4D in the file name and that ampersand at the end?
Perceival 40 is super important. It's a placeholder, so RASPA still knows to add a 4-digit number at the end of each picture's file name. You'll get frame 0001.jpg, frame 0002.jpg, and so on. Makes it easy to keep track of the frames. That ampersand at the end tells Linux to run the command in the background. That means you can close the terminal or do other stuff without stopping the time-lapse. Nice. So after 3 hours, I'll have a ton of pictures. How do I actually make the video?
A few ways to go about it. You can render the video right on the Raspberry Pi, but depending on your model and how many pictures you have, that can take a while. A lot of people just transfer the pictures to a more powerful computer for that part. But you can make a simple animated GIF right on the Raspberry Pi using ImageMagick, a tool you might need to install first using sudo apt-get install ImageMagick. Once it's installed, a command like sudo convert var www.frame.jpg animated.gif will combine all the pictures into a GIF.
And if I want something more professional looking?
FFmpeg is your friend for that. It's a super powerful command line tool that you can install with sudo apt-get install FFmpeg. You use FFmpeg with specific options to define your image sequence, the frame rate you want for your video, and what to name the output file. It gives you a proper video in a format like MP4.
Awesome. Time to switch gears. Let's talk high-speed photography. I'm imagining capturing things like balloons popping in slow motion.
Exactly. The Raspberry Pi camera modules, especially the newer ones like the V2 and the HQ camera, can record video at ridiculously high frame rates. That's how you get those awesome slow-mo effects when you play it back at normal speed. While the original software had limitations, updates have really improved high-speed recording. The standard modules can now do up to 90 frames per second, and the HQ camera can hit 120 frames per second under the right conditions.
That's incredible. I mean, those are tiny cameras. What's the catch?
Well, there's usually a trade-off. In this case, it's the resolution. To get those high frame rates, the camera uses a trick called pixel binning. It basically combines data from neighboring pixels on the sensor so it can read the image faster. The downside is you get a lower overall image resolution. For instance, to consistently hit 90 frames per second, you might need to go down to 640 by 480 pixels. It's a lot less detail, but it's often good enough for slow motion effects.
What kinds of things look really cool in high speed?
Things that happen super fast in real life, like dropping an egg onto something hard, crashing a toy car, or, yep, that bursting water balloon. The official guide even suggests doing the water balloon one outside.
Sounds messy, but fun. Any tips on setting these high-speed shots?
Stability is key. Even a tiny movement will be really obvious in slow motion, so you'll need a good tripod or maybe one of those helping hand tools with clamps. Lighting is also super important. Slowing down time means less light hits the sensor each frame, so make sure you have good lighting. Think about using a longer ribbon cable for your camera or even an adapter to extend the connection using an HDMI cable. That way, you don't have to keep the Raspberry Pi right next to the action.
And are there any special things to watch out for with the camera modules themselves?
Good point. With the original V1 module, the red LED lights up when it's recording. In high speed, that can cause annoying reflections, especially on shiny objects. A couple of ways to deal with that. You can cover the LED with something like a bit of modeling clay, or you can just disable it altogether. Add the line disable cameworld1 to the bootconfig.txt file on your Raspberry Pi's boot partition. You shouldn't have this issue with the V2 or the HQ camera modules. Their LEDs aren't as bad about causing reflections.
So to shoot high-speed video, what are the key raspivid commands I need?
The main ones are AFPS to set your frame rate, DIW and DH for the width and height. Remember, maybe go lower for those faster frame rates. DHT for the recording duration in milliseconds, R followed by the name of your output file, usually A.H264, and often NA to turn off the preview, as that can sometimes affect frame rates. For example, to capture 5 seconds of video at 90 frames per second and save it as test.h264, you'd use raspivid number in 5000 HFPS 90, number 640 HH480 marshal test.h264.
Nice. So can you take high-speed photography even further?
Absolutely. Think about adding a break beam infrared IR sensor to your Raspberry Pi. It shoots out an invisible beam of IR light, and when something breaks that beam, it sends a signal. You can connect that to a GPIO pin on your Pi. Then, using the Python PyCamera library, write a script that watches that GPIO pin. When the sensor detects motion, the beam breaks, the script triggers the camera to start recording high-speed video. Perfect for capturing super fast events that you wouldn't be able to time manually.
Okay, let's get into that Python control then. I know Python's huge with Raspberry Pi projects.
It is, and the camera library is super powerful. You can control pretty much every part of the Raspberry Pi camera modules with it. Most recent Raspbian versions have it pre-installed, but if you need to install it, just open a terminal and run. Sudo apt-get update to refresh the package lists, and then sudo apt-get install Python picamera, Python 3 picamera to get it for both Python 2 and 3.
And then how do I actually start using it?
Open up a Python IDE like Thonny, which comes with Raspbian. Make a new file, but whatever you do, don't name it pcamera.py. That'll clash with the library itself and cause problems. Choose something descriptive, maybe mycamerascript.py, or like in the guide, chafe5listing1.py. To show a basic live preview from the camera for 10 seconds, you'd write just a few lines. First, import the bits you need from the library. From pcamera import pcra, and from time import sleep. Then, you create a pcamera object.camera.pgra. To start the preview, use camera.startPreview.sleep10 from the time module keeps the preview on for 10 seconds, and finally camera.stopPreview to close it.
Wow, that's all it takes to get a live feed. You mentioned earlier that you might need to change some settings if you're using VNC.
Right. If you're using VNC to connect to your Raspberry Pi's desktop remotely, you might not see the camera preview. You'll usually need to enable direct capture mode in the VNC server settings on your Pi. Look for the VNC icon, right-click it, and choose Options. Then go to the Troubleshooting tab and make sure Direct Capture Mode is on. That lets the VNC server grab the camera output and show it on your remote screen.
What about changing the preview in Python? Can I rotate it or make it transparent,
Yeah.
like with the command line? You can totally control the preview in Python. To rotate it 180 degrees, just add the line camera.rotation equals 180 before camera.startPreview. And you can use 90 and 270 as well. To change the transparency, use the alpha parameter in Start Preview. Alpha goes from 0, completely see-through, to 255, completely solid. So camera.startPreview alpha 200 would make it kind of see-through. You can even control the position and size if you don't want it to be full screen. Just set full screen to false, and then use the window parameter, which takes 4 numbers, the X and Y coordinates of the top left corner, then the width and height of the window, like this. Camera.startPreview. Full screen, false, window 5150, 124, 576. That would make a preview window starting at 5150. That's 124 by 576 pixels. Okay, so we've got the preview going. How do we actually take a picture using Python?
Once you've created your camera object, you can grab a still image using the camera.capture method. Just give it the file path where you want to save the picture, like camera.capture homepdesktopimage.jpg takes a picture and saves it as image.jpg on the desktop. It's a good idea to pause for a few seconds using sleep before calling camera.capture, gives the camera's auto exposure and white balance time to adjust to the light, and gives you a better picture.
Makes sense. What about automating taking multiple pictures with Python?
Easy. Python's looping structures, like the for loop, are perfect for that. Say you want 5 pictures with a 5-second delay between each. You'd use a for loop with a range of 5. Inside the loop, you'd first call sleep5 for the delay, and then call camera.capture to take and save the picture. You can even use string formatting to give each picture a unique name, like this for iinrange5.sleep5, camera.capture, homepdesktopimage%.jpg, sleeksys.%ii. The percent gets replaced with the loop counter, so you'd end up with image0.jpg, image1.jpg, image2.jpg, and so on.
That's great. What about controlling all those camera settings we talked about? Brightness, ISO, exposure mode. Can I do that in Python?
Almost all those settings are attributes of your camera object. You just set them to what you want. Like for brightness, you'd use camera.brightness value with a value from 0 to 100. 50 is the default. Same idea for sharpness, contrast, and saturation. Camera.sharpness value, camera.contrast value, and camera.saturation value. They all go from -100 to 100, with 0 being the default. You can set ISO with camera.ISO equals value. Use 0 for auto ISO or a specific number like 100, 200, 400, etc. Exposure compensation is camera.exposure compensation equals value, -25 to 25. For exposure mode, it's camera.exposure mode, replace mode with auto, night, sports, just like the affixx switch on the command line. For metering mode, it's camera.hrmode mode, white balance is camera.autob mode, rotation is camera.rotation angle. You got camera.hrflip, true false for horizontal flip, camera.vflip, true false for vertical flip. You can even define a region of interest with camera.crop, x start, x with high height, with values from 0.0 to 1.0.
Wow, it's all right there in Python. What about setting the resolution for pictures and video?
For that, use camera.resolution. You give it a pair of numbers, width, and height in pixels. For example, camera.resolution equal 10024 768. Again, don't forget those max resolutions. For the camera module V2, you might need to give more memory to the GPU in the bootconfig.txt file if you want to use the full resolution.
I'll keep that in mind. And what about those image effects? Can I use those in Python?
Of course. All those fun effects are in Python too. Just use camera.imageEffect and set it to the name of the effect you want. For instance, camera.imageEffect color swap, camera.imageEffect sketch, camera.imageEffect cartoon. You can even add text to the preview or captured images using camera.annotate text.
Super handy. How do I record video with Python and PicCamera?
Use camera.startRecording, giving it the path to your file, like camera.startRecording video.h264 player. To stop, use camera.startRecording. Use sleep from the time module between those two to control how long the video is. The video will be saved as a .h264 file, which you can play with aux player or VLC. You might need to convert it to MP4 sometimes, which you can do with a tool like MP4box. You can also use this to adjust the frame rate. Oh, and there's camera.video stabilization. Set it to true to enable video stabilization during recording.
So many possibilities. Okay, let's look at some of those cool projects. First up, stop motion animation and DIY selfie sticks.
These projects show how you can physically interact with the Raspberry Pi camera. For stop motion, you want the camera ready to take individual pictures, and you move the subject a little bit between each shot. A button gives you control over exactly when to take each picture. And with the selfie stick, you can use a button connected to the Raspberry Pi and the camera as a remote shutter button.
Sounds fun. What kind of hardware do I need?
For both projects, you'll need a momentary push button and some jumper wires to connect it to the Raspberry Pi's GPIO pins. A common setup is to hook up one side of the button to a GPIO pin, like GPIO 14, and the other side to a ground GND pin. When you press the button, it closes the circuit, sending a signal to the GPIO. For the selfie stick, you'll obviously need longer wires so you can hold the button comfortably and, well, a stick. If you don't have it already, install the GPIO 0 Python library. It makes using GPIO pins super easy. You can install it with sudo apt-get install python GPIO0 python 3 GPIO0.
What about the code? Is it similar for both projects?
You got it. For stop motion, you usually want a preview to help you set up each shot, and then pressing the button saves the picture, maybe with a timestamp. For a selfie stick, you just want the button pressed to trigger the capture. The code in the guide for this stop motion project uses a continuous preview. When it senses a button press, using GPIO0, it grabs a picture with.